Hello friends. An elegant way of representing mechanical behavior of any material involves graphical representation. So when we talk about mechanical behavior, it has two components associated with it. One is the mechanical condition that we impose, and the other is the response of the material to the given mechanical condition. So whenever we talk about the mechanical behavior, it has two components. One is the condition, the condition that we impose, and the other is the response of the material to the imposed condition. Now the simplest condition that we can think about is the uniaxial tensile loading. And when you impose the uniaxial tensile load, a specific category of materials called metals and alloys, they behave in a rather characteristic manner, and their response is in such a way that we can capture the trend and use it to represent the behavior of all the metals and alloys. So this response of the material, this characteristic response of metals and alloys for the uniaxial tensile loading can be graphically represented by considering a two-dimensional plot with the response along the x-axis and the condition that we impose along the y-axis. So this condition, when we are talking in terms of the mechanical behavior, or we are talking about the mechanical condition, so the mechanical conditions are usually or invariably associated with force, and this force is referred to by the term load. So the condition involves load, and the response involves the change in the longitudinal dimension of the material, that is dl. So the change in the longitudinal dimension of the material is nothing but the length of the material for a given load minus the initial length of the material. So when we plot the mechanical behavior of metals and alloys for under uniaxial tensile loading, we get a characteristic curve of this form. It has a linear region which is followed by a non-linear but monotonically increasing curve, and finally we have a section that represents a monotonically decreasing curve. So the characteristic response or the characteristic mechanical behavior under uniaxial tensile loading by any metals and alloy can be represented by the specific curve here. It has three sections: a linear section wherein the load is directly and linearly proportional to the response, that is the change in the longitudinal dimension or the elongation of the material. In the second section there is a proportionality, but there is a non-linear proportionality, and in the third section there is an inverse proportionality between the response and the condition that brings about the response. Now when you consider this section alone here, so let me use a different color to highlight it. When you consider this section alone, it is characterized by the linear proportionality between the load and the response, and the proportionality constant that is involved is what we refer to as the stiffness, and it is also referred to as the Hooke's constant in remembrance of the researcher who established this relation. Now a better way of representing, when we say a better way of representing, but of course it is not objective but it is subjective, so a different way of expressing the same mechanical behavior rendered by the metals and alloys would be replacing or having a different parameter to express the condition and a different parameter to express the response. So we are going to do the same, but we are going to rather discuss the mechanical behavior of metals and alloy using the same framework or using the same graphical representation. But what we can do is we can replace the parameter, that is load, that we so far have used to describe the mechanical condition that we have imposed, and also we can replace the elongation, the change in the longitudinal dimension, with another suitable parameter to discuss the response. Now one appropriate candidate for replacing the load is stress, which is nothing but the ratio of the load to the original cross-sectional area of the sample on which we are imposing on the uniaxial tensile loading. So if we assume that we are imposing a uniaxial tensile loading on a cylindrical specimen and the cross-section area of the specimen is A0, then the corresponding stress that we impose on the specimen, or we can also say that the resistance that is offered by the specimen per unit area is the stress, and that stress is nothing but the ratio of the load and the cross-sectional area, the original cross-sectional area of the specimen. And in the same way, another alternate way of representing the strain would be, or rather the elongation would be the strain, and the strain is the ratio of the change in the longitudinal dimension to that of the original dimension of the specimen. So what essentially we are doing is, we are taking the ratio of the mechanical condition that we are imposing to that of a constant, and also in case of the response or in case of the strain, we are taking the elongation that is rendered by that the material in response renders to the imposed mechanical condition, and we are taking the ratio of it with respect to a constant. The constant in case of stress is the initial cross-sectional area. In case of strain, it is the initial longitudinal dimension. So what we are doing is, we are replacing these parameters, these two parameters, with a suitable parameter, which is nothing but the ratio of this original parameter to that of a constant. So we are just taking the ratio between a given parameter to a constant. So in that case, the reason we need to emphasize on this point, that is, we are considering a constant as a denominator, because in that case, when we replace these parameters with the suitable ones wherein only the constants are involved, it means that the overall trend of the curve is not going to change. Even though the exact values might change, the overall trend will remain the same, because the parameters that we are replacing the load and elongation with, they are nothing but their ratio of the original parameter with a constant. So therefore, even though the exact value might change, the overall trend will remain the same. So therefore, when you now plot the characteristic mechanical behavior rendered by a metal or an alloy, instead of now load and elongation, when you plot in terms of the stress and the strain, what we would end up having is, we would end up having a curve of the similar form, wherein you have an initial linear region which is followed by a non-linear but a proportional region, and finally a non-linear but inversely proportional region. So the overall trend remains the same, because the parameters that we have replaced load and elongation with, we once just considered, they are just normalized by a constant. In one case it is the cross-sectional area of the specimen, and in the other case it is the initial longitudinal length. So initial cross-section, initial longitudinal length, both are constant, so you are normalizing it. That means the trend remains the same. Now again, let us focus on the first section, the first linear section. So in this section, similar to the load and elongation, what we have is a linear relationship between the stress and the strain. So this Greek letter is used to indicate the stress, sigma, and epsilon, a different form of epsilon is used to represent the strain. So there is a linear relation between the stress and the strain in the elastic region. So we have an elastic region similar to the one that we observed in the load elongation representation, and because again the way we replace the parameters. Now the concept of proportionality, when we have stress and strain describing the mechanical behavior of materials, the concept of proportionality is capital E, which we refer to as the Young's modulus or modulus of elasticity. So when we considered load and elongation, there was a constant of proportionality. It was stiffness or Hooke's constant. In case of stress and strain, we have a constant of proportionality. It is Young's modulus or the modulus of elasticity. Now the question is this Young's modulus a behavioral parameter? Is this Young's modulus a parameter that discusses the behavior of a material or is it a material property? So is this Young's modulus a parameter that discusses the behavior of the material that varies for a given material with the dimension? Is it such type of a parameter, or is it such type of factor, or is it a factor that describes the material property? Now, in order to answer the question, we need to consider the context in which the Young's modulus appears. So the context in which the Young's modulus appears, the description in which the Young's modulus appears, is when you consider or when you represent the mechanical behavior in terms of stress and strain. It is only in this context you have the appearance of the Young's modulus, because when you consider load and elongation, the equivalent constant we have is the Hooke's constant or the stiffness. So the Young's modulus appears in the context when you have the stress and strain. Now, the fundamental reason, the primary reason for introducing stress and strain is because we want to get rid of any influence of the dimensions of the sample. So we have when you consider the sample of different cross-sectional area, they disturb or they bring about their own influence on a given load that we impose. And the same goes for the dimension and how it influences the longitudinal length and how it influences the elongation. So therefore, the primary reason we introduce the stress and strain instead of load and elongation is because we want to get rid of the influence of the dimension on the behavior of the material. So whenever we are discussing the mechanical behavior in terms of the stress and strain, what essentially we are doing is we are talking purely in terms of the material behavior alone. We are not considering the dimensional aspect of the material. We are not focused on, or this way of description does not include the influence of the dimension. Now, when you consider, for instance, failure load, which is a property of the material, depending on the dimension, the cross-section of the cylinder that you consider, the load required for failure varies. However, when you consider the failure stress, irrespective of whatever concentration you take, because you are normalizing the load with the initial cross-sectional area, the failure stress now is independent of the initial dimension. So whenever you are involving stress and strain, you are getting rid of the property or the influence of the dimension, and you are exclusively talking about the behavior of the materials. Now, one way a behavior of the material can be translated to or can be identified as the property of the material is when we are able to identify a distinguishing feature. So the reason we are able to talk about failure in terms of failure stress is because failure is one distinct form of a behavior. So because we are able to distinguish failure from all the other general behaviors, we are able to relate it to the corresponding mechanical condition that brings it about, and therefore we can refer to something as the failure stress and call that as a material property. So when you have a specific material, we can say at this particular stress the material would fail, and that becomes the material property. The reason it becomes a material property is because we have identified a specific form of the behavior. So identifying a distinguishing behavior, identifying a specific form of behavior helps us relate it to the corresponding stress. So here the material fails, and now it is possible for me to relate it to the corresponding stress, and this stress becomes the failure stress. So irrespective of what my initial cross section of my cylindrical sample might be, if the cylindrical sample is made up of the same material, then every time I impose the uniaxial tensile loading, that material would fail at this stress. So it means that whenever I'm able to identify a distinguishing feature, then it enables me to translate it to the property of the material. It's no longer the behavior of the material. When I relate it to the corresponding load, it helps me translate it into a property of the material. So stress and strain, it gets rid of any influence of the dimensions, so it talks purely about the material behavior, and when I'm able to identify a specific behavior, then it becomes possible for me to identify the property of the material. Now, when you consider the Young's modulus, which is associated with the elastic region, and the Young's modulus is nothing but the constant of proportionality. So the constant of proportionality that relates stress to strain. I'm just rewriting this expression here. So when I do that, this expression here indicates that this Young's modulus is nothing but the slope of this curve. So we have a straight elastic region, and this straight elastic region has a specific slope, and this slope is nothing but the Young's modulus. So when you relate it to the expression for the straight line, that is y m to mx per c, and the c is 0 because of the nature of the curve. The m here is equal to the here, and the x is the strain and y is the stress. So therefore, in the straight line, the slope represents the Young's modulus. Now what we have is, we have a characteristic behavior, that is, an elastic behavior is a characteristic behavior, and in that there is a specific slope associated with this material, and that slope is referred to as the Young's modulus. So we saw that in order to identify, in order to relate a specific behavior to the material property, it has to have a distinguishing feature like failure. So in elastic region, we have a specific behavior called the elastic behavior, and that elastic behavior is represented by the straight line, and this straight line is distinguished by its slope. So this distinguishing feature, the slope of the straight line, is nothing but the Young's modulus. So therefore, what we have identified is a specific behavior of a material, and we have identified a way of representing the specific behavior of the material, and therefore we can safely say the A, rather E, which is the Young's modulus, is a property of the material. It's a property of the material. So whatever may be the dimension, when you consider a specific material and represent it in terms of the stress strain curve and the mechanical behavior of the material in terms of the stress strain curve, and you observe that there is an elastic region, the slope that you get, irrespective of the dimension that you take, will remain the same, indicating that this slope originates essentially from the material. So therefore it is a material property. The way we have arrived at is, we have seen the context in which it appears, the context, that is stress and strain, which gets rid of any influence of its dimension. And secondly, the Young's modulus appears in a specific region, that is, appears in a specific distinguishable behavior, that is the elastic behavior. It characterizes the specific behavior, that is the slope of this curve, or the slope of this straight line. So therefore, Young's modulus is the property of the material. Now, the reason we need to insist on this fact that the Young's modulus is property of the material is because we have seen that Young's modulus is nothing but the ratio of stress to that of the strain. So the stress again is load, the ratio of the load and the original cross-section area of the specimen, and strain is the change in the longitudinal dimension of the specimen to the original length of the specimen. So these are the expression related to the stress and strain. Now when you introduce these expressions here, we end up with a relation of this sort. So we are just combining these two, or rather it should be so this would be the expression for the Young's modulus when you represent it in terms of load and the elongation. Now the condition that allowed us to arrive at this plot is, we have imposed a uniaxial tensile loading. So in this case, to arrive at this plot, we have imposed a uniaxial tensile loading. So in response to the uniaxial tensile loading, the material has elongated. So the longitudinal dimension of the material has increased. So the condition that we have imposed is uniaxial tensile loading. So it's a tensile loading along the axis of your sample. So uniaxial tensile loading. So this means there is an elongation associated with your sample. So the sample responds by elongating. So L, this response in response to the load, and L naught is the original dimension. So L will be greater than L naught. For uniaxial tensile loading, L will be greater than L naught. So when you have L being greater than L0, then dN will always be greater than 0. So in that case, you have dL, which is always greater than 0, A0, which is the original cross section of your sample, always greater than 0. The load that you are imposing, of course it's positive, so greater than 0. L0, the original longitudinal dimension of your sample, so it is also positive. So ultimately, when dL is positive, the Young's modulus is also positive in nature. So what you essentially have is, for a uniaxial tensile loading, the slope, of course from the slope it is possible for us to understand that the Young's modulus is positive, and also from this we can say that the Young's modulus will also be positive, because when you impose a uniaxial tensile loading, in response to the tensile loading, the material would expand, so the longitudinal dimension will increase. So this value here will be positive, and correspondingly, since all the other values are positive, the Young's modulus will also be positive. Now let us consider uniaxial compression loading. So we are now intending to study the mechanical behavior of a material, particularly metal and alloy, under uniaxial compression loading. So when you have a cylindrical sample of this sort, the uniaxial tensile loading will be something like this. Now we want to study the behavior of the material, the same behavior of the sample made up of the same material under uniaxial compression, which is written in this, or which is expressed in this form. Now when we do that, the first key factor that changes is the response of the material. In response to the uniaxial tensile loading, we saw that the sample, it expands. So the length assumed by it, once you start imposing the load, is greater than that of its original length. So under the uniaxial tensile loading, the length assumed by the sample, once you start to impose the load, is greater than the original length of the sample. On the other hand, when you begin to impose an uniaxial compressing load, that is indicated in green arrows here, the length assumed by the sample is less than that of the original length. So when the direction of the load changes, the length, when you start imposing the load, it shrinks, the overall sample it shrinks, so therefore the longitudinal dimension of the sample is now less than its original dimension. Now in this case, when you calculate the change in the longitudinal dimension, that is L minus L0, in this case, this change in the longitudinal dimension is less than 0. So it is negative in nature. So what essentially you are doing is, you are changing the direction of your loading condition, and you want to study the mechanical behavior of the material, but you notice that once you change the direction, the response of the material also changes, and particularly the elongation that ultimately helps you to relate it to the strain becomes negative now. Now when you consider as it is the elongation and substitute it here under uniaxial compression, this term becomes negative. We have seen under uniaxial compression, this term becomes negative. All the other terms remain the same. This is a constant because it is the cross-sectional area, initial cross-sectional area of your sample. This is the constant, that again it is the initial cross-sectional area of the sample, and this is the load that you are imposing. So you are imposing a load, so that is positive in nature. So ultimately what you would end up having is, for uniaxial compression, you will end up having an Young's modulus that is negative or less than 0. So at the bottom line here is, you are talking about a material property called Young's modulus, a material property that characterizes the behavior, the specific behavior of the material in the elastic region. Or to put it simply, you are talking about a factor, a parameter, a constant that describes the elastic behavior of metals and alloys, but you find that under tensile loading, uniaxial tensile loading, it is positive. Under uniaxial compressor loading, it is negative. So you cannot discuss or describe a material property that for this condition it is positive, for this condition it is negative. So how can we get rid of this disparity because of the difference in the loading condition? So this is where a new way of, or rather a non-technical aspect of this whole discussion comes into play. This non-technical, or rather a traditional way of viewing the loading condition comes into play, and this we refer to as conventions. So convention, as the name indicates, as we use it in our daily discussion as it's convention. So it means the same. The convention, the meaning of it remains the same wherever we use it. It comes from the tradition and how we have viewed things for quite some time. So the convention helps us get rid of this disparity, helps us talk about the material property, particularly the Young's modulus, irrespective of the direction of the loading condition. We are attempting to express the material property independent of the loading direction. So when we say Young's modulus is this value, we mean that this remains the same for both uniaxial tension and uniaxial compression. So this conventions helps us achieve that. So how they do it is by simply assuming that whenever you are talking about tensile loading, so convention, it doesn't usually, they don't require any justification. So convention is, we've been doing it for a while now. If you assume it, things would make or the way you would describe this property would be easier. So that is the reason why we have conventions, why we have traditions. So it makes our discussion makes our life a bit more easier. So we just have to understand it, and we just have to know that, and we just have to adapt it in our studies. So according to the conventions, particularly in the context of our loading conventions, the tensile load is always assumed to be positive, and the compressive load is always assumed to be negative. So whatever value you have, even though in the machine, while you are setting up your machine, you are imposing a positive load, you are imposing a load of certain newtons, when you are discussing it or when you are writing it down on the piece of paper, you need to include this negative sign for the compressive load and the tensile load, because it is often the mechanical behavioral studies, they begin with tensile loading, it is treated as positive, and compression is rather treated as a deviation from the conventional studies. We use the negative sign here. So the positive sign is assumed for the tensile loading, and for the compressive loading we assume a negative sign. So once you assume a negative sign for the compression, then we have the expression for the Young's modulus, that is expressed, or that is written as E naught. So this is the expression for the Young's modulus. Now for the uniaxial compression, we saw that this is negative, and since by convention, because of this convention here, since the load also assumes a negative value, so it's just that the value remains the same. So the value comes from the machine that you are using to impose the load, so that remains the same. All that you are doing is, while writing or while estimating the corresponding Young's modulus, you are introducing the negative sign for the load. So that means you have a negative sign in the numerator that comes from the convention, and a negative sign in the denominator that comes because of the response of the sample. Because the sample shrinks, you have a negative sign. So both these gets cancelled out, and ultimately what you would end up having is an Young's modulus that is positive, and this positive Young's modulus comes from uniaxial compression testing. So what we have is, we have an Young's modulus that is rendered by uniaxial compression testing, and we have also an Young's modulus that is rendered by the uniaxial tensile testing. Both these are of the same material, and both these are so they have been gathered from the stress strain curve. So ultimately, since the Young's modulus, it is a property of the material, irrespective of the loading conditions you have, we get the same value. So but for the conventions here, what we would have arrived at is an equal but a reversed value for the Young's modulus under compression. So the convention helps us have an equal value, an identical value for tensile and compressive testing. And even if you try to plot it without the convention, when you try to plot the behavior of the mechanical behavior of the material without the convention, you would find that the curve is not along in the first quadrant, it's not in the positive quadrant, it would have shifted, and that makes the whole understanding of the different sections quite difficult. So the conventions, like tradition, help us in few things, simplifying few things. Great. Now, so far what we have seen is, we have seen that there is a constant of proportionality when we relate the mechanical behavior and the response of the material, particularly metals and alloys, in the context of stress and strain. This constant of proportionality, it is different from the constant of proportionality associated with load and elongation. There it was stiffness, here it is Young's modulus. The other name for stiffness is the Hooke's constant. Now, the other understanding we gained is that this Young's modulus, since it is quantifying a specific behavior, it is describing the specific behavior of the material, it is the property of the material. So, since it is the property of the material, irrespective of the loading condition we have, we need to arrive at a same value. We need to arrive at the identical value. So, in order to ensure that, even if we use tensile loading or compressive loading, we are able to arrive at the same value, we use convention, and this convention states that for compression, the load that you are imposing should be negative, even though the value might be positive. So we need to add a negative sign to it, and in the same way for tensile it should always be positive. So whenever you are reading or whenever you come across a load and it is mentioned as a positive value, it means it's a tensile load, so wherever it may be. And in the same way, if it is mentioned in the negative terms, and the load is mentioned as using a negative, or it is prefixed by a negative term, the negative symbol, it means they are talking largely about the compressive load. So now let us consider or discuss the Young's modulus from a different perspective, considering that this is a property of the material. So let us consider or discuss or try to understand or arrive at what this Young's modulus is from a different perspective. So the perspective that we can arrive at this property is from the atomistic view. We will start from the atoms and we will see what from the atomistic level this particular Young's modulus means. So what is Young's modulus when we are talking in terms of the atoms? So when we are going down and down along the length scale and we reach the atoms of the metals that we are talking about, and we want to see what is the Young's modulus means in this atomistic scale. Now when we are talking about the atomistic scale, so anything below that will not be in the realm of metallurgical and materials engineering. So anything below the atomistic scale will be part of quantum physics or quantum mechanics, so that will be a quite different realm. Of course we have ways to connect to it as well, but any discussion, particularly an engineering oriented discussion, it stops in the atomistic scale, so that is where we stop. So now when we talk about the atomistic scale and we want to understand what an Young's modulus is from the atomistic perspective, let us begin by considering a simplistic case of two atoms. So these two atoms, since we are talking or largely focusing in terms of metals and alloys, so often in metals and alloys we largely have a base metal, a metal that acts as the solvent, and we have alloying elements that act as the solute. So let us assume that these two atoms are identical atoms, so meaning they are of the same metal, so they belong to the same metal. So let this atom be A and let this atom be B. Now the interaction between these atoms, it stems from the subatomic particles. So the atom itself, they do not interact with each other. The interaction, it comes from the subatomic particles, and these subatomic particles, that is the electrons, the protons, they have a specific charge associated with it, and of course you have uncharged neutrons. So for this discussion, since we are focusing on the interaction between the atoms, the interaction essentially stems from the electrons and protons. Now when you have interaction of these like and unlike charges, there is a specific way of describing this interaction energy. So whenever you have the charged particles, and these charged particles are interacting with each other solely because of their charges, there is a way of quantifying the energy associated with this interaction. So we are talking about interaction energy of the subatomic particles between A and B. So the generalized expression, this interaction energy is, so let us call this as interaction energy, is directly proportional to the product of the charges. So QA and QB, so the product of the charges. So QA is the charge of the subatomic particle that is interacting from the atom A to that of the subatomic particle in the atom B. So we have the charges of the interacting subatomic particles. So the interaction energy is the product of these charges. It is proportional to the product of the charges, and this interaction energy is also inversely proportional to the distance separating these charges. So we are talking about the interaction between two atoms. So essentially, when we say interaction between two atoms, we are talking about the interaction between the subatomic particles. This interaction stems from the charges of the subatomic particles, and this interaction energy is proportional to the product of the charges and inversely proportional to the distance separating these subatomic particles. Now, when the interaction is between the like charges, say the like charges are positive, and the unlike charges are negative and negative. So when we have such an interaction, so the product is always positive. So when you take the like interaction between the like charges and you consider the product between the charges, it is always positive. And in the same way, since you cannot have non-zero distance separating the particles, so this R, the distance separating the atoms, is also positive. So for interaction between the like charges, the product is positive and invariably R is positive. So the interaction energy for the like charges is always positive. It is greater than 0. So the interaction charges, which is proportional to the product of the charges and the distance separating them, is always greater than 0 for, this is for the like charges. Now if you reverse and if you consider the interaction between the unlike charges, it will be between positive and negative charges. So the interaction between the unlike charges would be between positive and negative charges. So it means the product here will be negative. So therefore for unlike charges, the interaction energy would be less than 0, because R again can only be positive, it cannot be negative. So essentially what we have is, we have like and unlike charges, and depending on the interaction or depending on these two interactions, the interaction energy can be positive or negative. For the interaction between the like charges, the interaction energy is positive. For the unlike charges, it is negative. Now the like charges, they repel, whereas the unlike charges, they attract. So the interaction between the like charges is repulsion and the interaction between the unlike charges is attraction. So it means the repulsive energy, which is again the product of the corresponding, which is proportional to the product of the corresponding charges and inversely proportional to the distance, is positive, whereas the attractive, or the energy of attraction or attractive energy, whatever you might call it, is negative. Again, it is, the formulation is the same, the product of the corresponding charges and the distance separating them. Now it is possible for us to plot how the attraction and the repulsion energies would look like when the distance separating the charges changes. So what we want to do is, we want to render a graphical representation for the attractive and the repulsive charges. So repulsive, we will denote it by the red, and so repulsive will be denoted by the red, and the attractive charges will be denoted by green. So what we want to do is, we want to graphically represent how these energies, the repulsive energy and the attractive energy, or the energy of attraction, would vary when the R changes. So we want to change the R, and we want to see how the energy of attraction and the energy of repulsion would vary. Now since the energy of repulsion is positive, it will occupy this quadrant of your plot or your coordinate system. Since the attractive force, or the extractive energy rather, not the force, energy is negative, it will occupy this quadrant of your plot. Now in that case, irrespective of the quadrant that we are plotting, the attractive energy and the repulsive energy, since the formulation is the same, the nature of the curve remains the same. So the repulsive force will adapt a form like this. So as the R decreases, the repulsive force keeps on increasing, and as the R gets close to 0, this force turns infinite. So it turns infinite. So as the R get close to 0, be it repulsive energy or attractive energy, the interaction energy as a whole, it turns to infinity. So that is the nature of the curve that we have here. Since the formulation is the same, we will observe the same trend, but because the attractive force is or attractive energy rather is a negative energy, the trend will be the same but will be reversed, and we will observe it in this quadrant here. That is, as the R increases, the negative attractive energy increases, and as the R gets close to 0, it reaches infinity. So here the red curve indicates the repulsive force. As the R increases, the energy increases, and as the R gets closer to 0, the energy shoots to infinity. In the same way, as the R increases, the energy negatively increases for the attractive force, and when it gets close to 0, it shoots to infinity. So you have your positive infinity here, you have your negative infinity here, and we are talking about the interaction energy. Now, this is how we are able to graphically represent the behavior, the interaction energy between the two different atoms A and B. Now, what we are considering is not just the interaction between the like and unlike charges separately. We want to have a representation that combines both the attractive energy and also the repulsive energy. So far, this plot here, it talks about the interaction energy. This plot here, it talks about the interaction energy of the like charges separately. It talks about this plot here, it talks about the interaction energy between the unlike charges separately. However, what we are interested is in the interaction of the two atoms that comprises of both like and the unlike charges. So when we want to talk about the interaction energy of the atoms, two different atoms as a whole, then we need to combine both the repulsive energy and the attractive energy. So these two plots, they talk about the interaction between the light charges separately. That is, the red curve, it talks about the interaction between the light charges separately. The green curve rather, it talks about the interaction between the unlike charges separately. But the atom as a whole, it comprises of both like and the unlike charges. So combination of these two will give you the interaction between the entire atoms. So in that case, the interaction between the entire atom adapts a specific form like this. So it adapts rather an unsymmetrical form like this, and this is nothing but the interaction energy of two atoms that is dependent on R. So this is a plot. By summing up these two curves, we end up with a curve like this. Now, the reason this curve is not symmetrical, it is unsymmetrical and it extends as R increases, is because the attractive energy is a long range energy, whereas the repulsive energy is a short range one. So the attractive energy is a long range energy. The interaction between the unlike charges, it is established over a long range, whereas the interaction between the like charges, it exists only in the short range. So therefore you have a characteristic curve of this sort. So now we have interaction energy between two atoms, and this interaction energy, it depends on the position of the atoms. So therefore it is referred to as the interaction potential. So the reason we call this as interaction potential, so what essentially this curve indicates is, so when you bring two atoms close together till certain point, the energy that is established between the two atoms keeps on decreasing. So till certain point, the energy between the two atoms keeps on decreasing. At a specific point, it assumes a minimal most value, and beyond that value, if you keep on bringing them closer, the energy between the atoms keeps on increasing till it reaches infinity. So that is what this curve indicates. So this curve talks about the interaction energy between two atoms, and since this interaction energy is based on the distance separating the atom, is based on the position of the atoms, it is referred to as the interaction potential. So it is generally represented by P. So since we have already introduced the parameter P for load, so we are using this fancy looking P, and since it is dependent on the position of the atom, so we write this as fancy looking P as a function of R. So in this discussion, this indicates the interaction potential. So interaction potential is the fancy looking P, which is dependent on R. So this is how the interaction potential, the energy between the atoms, when you change their position, when you bring these atoms close together, or when you move them apart. So this is how the energy between the atom changes. So they assume the lowest point at a specific distance. So the energy between the atoms is the lowest at a specific point. So this specific point, or this specific position at which the energy between the atoms is the lowest, will often translate to the bond length. So when you are considering the crystalline arrangement of the atoms in a metal or an alloy, it is dictated by, or it is governed by, the bond length. So you are able to construct a unit cell that represents the crystalline arrangement of the atoms, and in that unit cell you have specific distance between the two atoms, and that specific distance is referred to as the bond length, and that specific distance is dictated by this interatomic potential, and the point wherein the interatomic potential energy is the lowest corresponds to the interatomic distance in the given unit cell. And there is a lowest energy that is assumed by the atom at its stable point or the equilibrium point, and it is expressed in this way. And this lowest energy assumed by the atoms, that is the lowest interatomic potential that is assumed by the atoms, it translates to bond energy. So the distance that relates to the lowest energy translates to bond length. So the distance wherein the atoms are in their stable state, it relates to bond length. The energy assumed by the atom in this stable state, it translates to the bond energy. So what we mean by bond energy is, when we want to move the position of the atoms away from this lowest energy state, we are moving it towards a high energy state. So that means when your atom assumes a lowest interatomic potential energy, so when it assumes a lowest interatomic potential energy, then you need to impose a load or impose a force to change its position. So lower your interatomic potential energy, lower or higher will be the load that is required to move the position of the atom from the stable state. So the more lower this position is, more lower the interatomic position, or interatomic potential energy of the atom is, more lower this particular value is, the more load will be required for us to change the position of the atoms. To bring about any change, to bring about any response in the material, more load should be imposed by us in order to bring about this change. So this is one of the critical understanding we gained from the atomistic view. So what we have so far seen is, we have considered two atoms, we have considered the interaction between the atoms, but this interaction leads us to an understanding of the position of the atoms in a crystalline system, the position of the atoms in a metal. Now when we want to elongate this metal, we want to move these atoms from its position, but this position is associated with the lowest energy. So more low is the energy, so more lowest is the energy, you need more load to bring about the change in the position of the atoms. So therefore, from the atomistic perspective, where we stand now, from the atomistic view, we are able to relate it to the mechanical behavior of the material. Supposing there is a material with an interatomic potential of this form, so let me use a different color, with an interatomic potential of this form. So let's say the black one is the material in the black is A and the material in the black is B. For A, the lowest energy at the bond length is much low when compared to that of B. So the energy at the bond length R0 is much low when compared to B. So therefore, when you want to move the atoms from its actual position, from its bond length position, you will need high amount of load for A when compared to that of B, because in A, the atoms are sitting in a more comfortable position. It's the lowest energy state when compared to that of B. So therefore, you need to impose more load in case of A when compared to that of B. So therefore, even from an atomistic perspective, it is possible for us to gain an understanding on the mechanical behavior of the material. So from this, we will build and try to understand how this understanding or how this perspective ultimately leads us to the understanding of Young's modulus. So we will wind this lecture up here, wherein we are able to see the discussions in the atomistic scale will help us relate to the mechanical behavior that we have been considering so far, and in the next lecture we will try to relate it to the property that we are interested in, that is the Young's modulus. Goodbye.